Hello everyone, we are from Group 9 and we will be presenting about the pressurized water reactor or PWR inside of a nuclear power plant. In a PWR, we basically have two cycles, which are the primary cycle and the secondary cycle. In the primary cycle, we have the pressurized reactor and the steam generator. The secondary cycle, we have the turbine, generator, and condenser. In the pressurized reactor, uranium-235 isotope atom undergoes nuclear fission, and this reaction releases a lot of energy in the form of heat. The heat produced from this reaction heats the water inside of the reactor to approximately 327 degrees Celsius. The water here is kept at a high pressure of about 15 megapascals to avoid boiling. This heated water then flows out of the pressurized reactor and comes in contact with the water inside of the steam generator. Water inside of this generator is not kept at a high pressure, hence when heat is transferred from the water with higher temperature, the water inside of the generator will boil and produce steam. The cooled water will be pumped back into the reactor for reuse. Steam produced from the generator flows to the turbine and rotates the turbine. The generator that is connected to the turbine converts the kinetic energy from the rotation of the turbine into electrical energy. Water from a reservoir flows into the condenser and comes in contact with the hot steam from the turbine. This will cause the steam to condense into liquid and will be pumped back into the steam generator to be reused. These are all the assumptions that we have made in order to solve the problem given, and this is our proposed schematic diagram. S1 enters the PWR and exits as S2, passes through a pressurizer and enters the steam generator. From here, we will have two outlet streams. S3 will be pumped back into the PWR while S4 will be used to rotate the turbine. The kinetic energy from the rotation of the turbine will be converted into electrical energy by the generator. From the turbine, we also have stream 5, which will then flow into the condenser. We have set a river as our reservoir, so water from the river will flow into the condenser through stream 8. From condenser, we have stream 6, which will be pumped back into the steam generator, and we also have stream 9, which will then flow into the river. This will be our primary cycle, and this will be our secondary cycle.
The overall energy balance and thermal efficiency analysis, I'm going to start with the turbine. So in the turbine, we need to produce 3000 megawatt of power. So from this value, we can find the mass flow rate of the secondary cycle using energy balance. Next, for the mass flow rate of the primary cycle, we can find it using the mass flow rate of the secondary cycle we find just now with the energy balance of the steam generator. For pump 1 and pump 2, we find the work required to pump the water circulate in respective cycle, also using the energy balance. While in condenser, we can find the mass flow rate of the coolant coming from the cooling tower, also using the same techniques. So for the overall energy analysis, we can find that in order to heat the feed water from T1 to T2, the PWR generate 11,303 megajoule of heat for every 1 second. So and for the secondary cycle, we can find that they receive heat 11,887 megawatt from the steam generator. So the power produced, which is the work produced from the turbine, is around 2,550 megawatt, and the actual power produced is the difference between the work turbine and the work pump, and we get 2,500.898 megawatt. From this value, we can find the thermal efficiency of the secondary cycle, which is 21%. This thermal efficiency is quite low because average thermal efficiency of nuclear power plant is around 33 to 37%. Due to inaccurate assumption, there are some considerations need to be taken, such as common PWRs can withstand about 150 to 160 bar with the operating temperature around 300 degrees Celsius. If the pressure limit exceeds the limit, there are high chances that the water will boil, therefore reduce the thermal efficiency of the plant. And at given pressure, the reactor cannot operate at higher temperature, therefore can limit the overall efficiency of nuclear power plant.
Moving on to the next part, which is the cycle that the power plant models do. The secondary cycle of the power plant is assumed to obey ideal Rankine cycle. This TS graph shows the actual process that is happening in the cycle. From stage 1 to 2, water in the secondary cycle will enter a pump and brought to a higher pressure. Then, from stage 2 to stage 3, compressed water enters the steam generator and turns into superheated vapor form. From stage 3 to 4, water in vapor form is brought to a lower pressure and temperature through a turbine and causing the water to turn into saturated mixture with quality close to 1. From stage 4 to 1, water enters the condenser and turns into compressed liquid. In ideal Rankine cycle, water at stage 1 should be in saturated liquid. However, in actual application, maintaining the temperature of the water to be constant throughout the condenser might pose a challenge, as higher rate of heat transfer between the coolant and the working fluid would contribute to the temperature drop across the condenser. Through application of Rankine cycle, we can actually improve the thermal efficiency of the nuclear power plant by manipulating some variables in the cycle. The first method that can be used is regeneration method by using closed-feed water heater. In this method, two new components are added in the cycle, which is the closed-feed water heater itself, which also acts as heat exchanger, and a mixing chamber. The main purpose of this method is to raise the temperature of the steam generator inlet so that lesser heat is required to turn it into steam to produce the same amount of work. The second method that can also be used to improve efficiency of the nuclear power plant is by applying reheat process. Similarly, another component, which is a turbine, is added to the cycle. So, there are two turbines now operating in the cycle. The first turbine is operating under high pressure, and the other turbine is operating under low pressure. The main objective of this method is to reduce the moisture content of the steam at the final stage of the expansion process, which is stream 6. If this stream leaving the turbine has higher moisture content, it may damage the turbine after some time. Besides, by reheating the steam before entering the condenser, more work can be produced. This can be shown in the graph, in which the area under the graph that represents the work done is greater than that of a normal Rankine cycle graph.
For conclusions, the pressurized water reactor has produced 13,789 megajoule of heat for every second it operates from all of the proposed schematic diagram, calculations, and assumptions made. The heat generated will heat the feed water from 250.24 degrees Celsius to 327 degrees Celsius at respective pressure. The steam produced by the steam generator is used to rotate the turbine connected to a generator, which transforms kinetic energy into electrical energy supplied to the city. This power plant has a net working output of 2,500.898 MW and a thermal efficiency of 21%. Finally, for recommendations, we will recommend using enriched uranium-235 as the nuclear fuel, because this reactor uses light water as the coolant and moderator. When natural uranium is used, it absorbs too many neutrons. The absorption by light water of too many neutrons will reduce the rate of nuclear fission and thus reduce the heat energy produced in the reactor. The fuel content of fissile uranium-235 must be increased by the uranium enrichment process. The last recommendations is using mechanical insulation on the pipes at the power plant to reduce heat loss and running costs. The network performance will increase by reducing the heat loss, and this will increase the thermal efficiency. So this is our reference we have used in completion for this integrated project. That's all from us. Thank you.